It's very nice to meet you through online, algebraic geometry in Asia. Today we have two talks. First talk will be given by Yuji Odaka from Kyoto University. He will speak on various geometric compactifications of moduli of K3 surfaces.
Yeah, so thank you very much for the invitation.
Let's welcome him, yeah.
Thank you. So thank you very much for the invitation and giving me this chance. It's my great honor. And and sorry for the trouble of the time. I forgot my meeting which I should attend. So the title is a bit vague, but what I'm going to talk is not does not lie in pure algebraic geometry. And well, some parts are really purely algebraic geometric, but some parts are involving non-variety compactification. But I mean it to be a canonical one in some sense, and geometric in some sense. So the more or less the former half is more algebraic geometric, and the latter half is a bit more, I would say, tropical geometric, but still it is directly connected to algebraic geometry. So let me begin. So let me start with a bit review of K-stability story. So K-stability means to be some version of GIT stability, but it does not involve embedding into projective space, but it's rather just a stability notion for polarized variety. And originally it's meant to be equivalent of existence of some canonical metric. So given a smooth projective variety, of course, there are plenty of infinite, metrics, even if you fix a Kähler class. But we want to ask if there's a canonical one, some unique one. So in the Riemann surface case, we have a unique metric with Gaussian, constant Gaussian curvature, and we want to ask the similar things in higher dimension. Then it turns out that from dimension 2 and higher, there are, in some cases, there do exist such a, here I formulate as a constant scalar curvature. So curvature is in general not a function in high dimension. So it doesn't make sense to say curvature is constant, but the scalar curvature is some reduced version of it, which is a function. So we can ask if there's a Kähler metric whose scalar curvature is constant. And the K-stability is now formulated by Donaldson in purely algebraic geometric way, scheme theoretic way. And before that, Professor Tian introduced a slightly more analytic version for Fan varieties. But anyway, the Yao-Tian-Donaldson conjecture, the famous one, predict that this should be equivalent. And now this is known to be true for so-called Kähler-Einstein case, which is in algebraic geometric term, the case when L is proportional to the canonical line bundle. So canonical line bundle is somehow A times A. L. This Kähler-Einstein class is when L is Kx numerically with some constant A. But of course, in general, K and L could be independent. So L stands for some polarization, and it plays a role to fix a Kähler class here. Yeah, which is essentially giving no information in curves case, but in higher dimension case, it does give it gives the information. Then this is a rather purely, this is about the existence of some canonical metrics or differential geometric story. But this K moduli, which is more or less the moduli of K polystable variety. So if you think of this kind of moduli, if you just collect the K-stable ones, then it really gives a good framework for the moduli. So including the classical ones. So during manifold quantification of during manifold moduli of stable curves, and well, like moduli of Calabi-Yau varieties, the smooth ones, and also a canonical polarized case, when the L is proportional to Kx. So this case when Kx is ample, so more or less it's a special case of general type. In this case, more or K ample case. So we have during manifold quantification and also KSPA moduli, Kohler, Shepard, Baron, Alexeyev moduli, which extend this TM story. And yeah, so also recently this another special case, a kind of opposite case, when L is minus Kx. This case, the existence of K moduli is also done. So the general existence statement is completed. And what I mean is that the K moduli exists as a projective scheme. This is done by, plenty of papers, like maybe more than 20. But so I cannot, give precise statement and all the references. But so I just mentioned that until 2014, I guess, or 15, we had the proof of a smoothable case using the differential geometry. But now, due to development of algebraic geometric side, we have a purely algebraic geometric proof. And the last piece was last missing piece was properness, which is solved by Liu Shu Juan, I guess, in the last month, and also which involves another piece of the properness is done by Brown, Liu, and Juan, and sorry, Lee, and I forgot the. Sorry, I shouldn't have mentioned, but anyway. So this is done. The existence is done. But in general case, it's far better. Good understanding. So Kerenstein case is more or less settled. But here, as you see, this is missing the case when A is 0. So which is nothing but the moduli of Calabi-Yau case. So that is the where we want to. That is what we want to discuss. So in case K0 case, the Calabi-Yau in some broad sense case, this K stability is equivalent to the log terminality, and the semi-stability is equivalent to semi-log canonicity. So, for example, in a curve case, KLT of course implies, requires normality. So, it's just does not allow degeneration. So it's just an elliptic curve, and well, in this SLC and K0 for one-dimensional case is nothing but an IN type degeneration. So in the IN type, in the sense of Kodaira. So like an n-gon of P1s like this. So here I wrote a picture of the case when n is 6, but any n is allowed. So if you go to K3 case, then the K-stable example include ADE degeneration, so or type 1 degeneration. And on the other hand, if you consider Kurikov degeneration of K3, which is simple normal crossing degeneration with K0, there are two types. So remember that there are two types. So type 2 degeneration, so let me mention this is type 2 degeneration, looks like looks like this. And here we have a rational surface. And here we have an elliptic ruled surface. And so these double curves, these are normal crossing and also elliptic curve. And this direction is P1. So these are ruled. The generic fibers of P1. And the type 3 case looks like well, I can only draw the kind of simplest one. So it looks like this. So it is still simple normal crossing, but and each pieces, the components are rational surface, and yeah, here we have P1 instead. Yeah. Yes, and if you consider dual graph or complex, intersection complex, dual intersection complex of it, then this becomes, if you consider this object, then this becomes S2. So you see S. So dual graph means that to each component we associate one point and connect them according to the way these components intersect. So yeah, we still have a dual tetrahedron, so which is homeomorphic to S2. And in this case, let's see. So in this case, oops, let me write in this pink color. So we have this kind of dual graph, which is topologically a segment. And this segment and S2 appear at the latter half of the talk for the compactification of K3, modular of K3. But anyway, here's a complication of the modular compactification color here. So even if you consider just a K-elliptic curve or K3 case, there's a subtle problem if you compare the with a case like Fano case and the K-ample case. So, or just a usual GIT story. So in GIT, every semi-stable object should degenerate to unique semi-stable one, which corresponds to a minimal orbit or closed orbit. And but in this case, this case, sorry, I forgot to mention this polystable, but the polystability corresponds to a semi-stability with a minimal orbit, I would say, in usual GIT story. So if you consider the stability of vector bundles or shifts, then it means that it's a direct sum of semi-stable with the semi-stable ones with the same slopes. But in the variety case, it's more or less correspond to that it allows a continuous automorphism. And yes. So in GIT setting, the semi-stable one always degenerates to unique polystable ones. So in Fano case, this is true. And this polystable K-polystability of Fano variety corresponds to the existence of, it's equivalent to the existence of K-Einstein matrix. So this was this K-polystability is an important notion for the differential geometric perspective. So it was the same for vector bundles version. Yeah, But in this case, K0 case, these semi-stable ones are often non-normal. So it's may not be reducible, looks like this. But the polystability is actually equivalent to stability in this case. And it does not allow non-normal ones. So it's irreducible. So in particular, semi-stable one cannot degenerate to polystable ones. So it is very different from the Fano case. And I mean, the usual GIT setting. Yeah, so here I wrote the problem. Semi-stable one does not degenerate to K polystable. And furthermore, even if you consider the elliptic curve moduli, so already the problem is clear there. So if you consider the degeneration of elliptic curve and require that the degeneration should admit only a semi-low canonical singularity, as it is written here, and K0, so that it is K semi-stable. Then it allows every IN degeneration for any N. So of course, the moduli of elliptic curve is just a J line, the classical, the classical J invariant. And so the only, reasonable compactification, the compactification of A1 should be, P1, at least if you require the P normality. So we know that the moduli, the moduli should be, compactification should be P1, but the problem is what do you want to parameterize? What do you want to parameterize at that infinity point, the boundary? So that is really non-trivial to me. One could say that it should be I1, which is just a rational nodal curve. But you can also degenerate. If you consider elliptic curve as a cubic curve, then it is also natural to consider the degeneration. It is also natural to degenerate to 3 lines, so which is I3. So there's ambiguity of N. Yeah, so this is a bit subtle problem. And but still, we want to consider a degeneration to, if you want to consider moduli of K stable ones and K semi-stable ones. So let's ask about the stable reduction in this K stability framework. So if you consider a family of K stable varieties or polarized varieties, then we want to consider K semi-stable degeneration. And here's one conjecture, which I have been only orally talking, not in the paper, but well, some partial results are published. Anyway, so in general, I expect that if you consider a polarized family and suppose, say, some fiber, some closed fiber is K unstable. Is K unstable, while the other general fibers are K stable. So K stable ones degenerate to K unstable. So then we want to replace that closed fiber by a K semi-stable one. Then here's a characterization of such stable reduction. So it's among such vertical birational transform, the fibers, the one whose fibers are all K semi-stable is parameterized by minimizing some invariant. And here the seam, I don't define the seam line bundle, but it is essentially an intersection number of this total space. But well, in general, to be precise, we should allow a base change to fill in a reasonable, K semi-stable filling. So we should allow find a base change and also divide that number by the, no, this is a normalization factor, divide by the degree. Yeah, so here's just this is a kind of digression of the talk, but yeah. And this is confirmed for basically K-Einstein case. This is completed. K0 case and K-ample case is done, and K-ample case is also done by Wanju, and Calabiao case is also done in my old paper, and also Buxom also knew it. Yeah. Anyway, yeah, this is a bit digression. So anyway, we want to consider, the K moduli story for Calabiao case, K0 case. And as I said, there's a, essentially unsolvable problem here, which is a fact. So so it's very subtle how to consider the problem. Anyhow, if you consider a partial compactification which corresponds to strict stability, so before I was focusing on K polystable ones, and also was thinking about K semi-stable degenerations. But if you consider a strict stability, which is actually, should be good. K stability should be equivalent. The strict K stability should be equivalent to K polystability and automorphism finiteness. So automorphism of this polarized variety, by which I mean automorphism of X, which preserves the class of L, should be finite. Yeah. So if you consider such a strict stable version, so those with only finite automorphism, then in Calabiao case, we still have a partial compactification, which is canonical. So let me first observe this. So first we fix a setup. So we consider some moduli of polarized Calabiao varieties. K trivial varieties, say like K3, a projective K3. And let me denote it by like this. And then it is not hard to see it exists as this moduli. I just wrote as if this is just a set, but this is algebraic space. Just by applying, just by quoting part of Hilbert's scheme and apply Kiri-Mori. And this is not so hard. And it is furthermore quasi-projective. So it is a more technical, difficult story of the feedback to put an ample line bundle on this algebraic space, so that we have a quasi-projectivity. So he proved by his method of weak positivity. And so this does not involve the GIT. And later, for a different story is that this should be obstructed from a different deformation theoretic perspective. So as a cos moduli, this should only admit the quotient singularities. So especially this is a normal variety. So this is normal quasi-projective variety. So these are known, several decades ago. And we want to consider the compactification of this. And before going on, let me also point out that there's a canonical metric called the Bay-Peterson metric, or generalized one. So the original Bay-Peterson is on the moduli for curves. So this is a generalization, but the Kähler class, the Kähler form is written in this way, where this is a holomorphic Borel form. Yes. And so this is our setup. And yes, so to each XL, so there's a canonical metric due to Yao, Calabi-Yau metric, whose Kähler class is C1 of L, and the Ricci curvature is 0. Yeah, maybe I should have explained it before this slide. Sorry. So each of X, XL admit a Calabi-Yau metric, which is a canonical metric. And so that this is K-stable always. So these are always K-stable. And we want to talk about the limit of the Calabi-Yau metrics on this XL. So of course there are many XL here, and we want to talk about the differential geometric limit. And here's a big theorem by Donaldson-Sun, proved like 9 years ago. So if it is not non-collapsing, this is a bit technical condition on differential geometry. So which roughly means that the limit has the same dimension. So in general, if you trace the behavior metric, the limit can go to something lower dimension. So this is a bit different from algebraic geometric intuition, because in algebraic geometry, the dimension of fiber usually goes up, but in differential geometry, it goes down. So if it goes down, then we call it collapsing. But usually, the collapsed limit, the limit whose dimension is less, is not a variety. So yeah, not a variety. But so this theorem says, as far as this is non-collapsing, then the limit of Calabi-Yau metrics should be still a variety. And in particular, this is a limit of Hilbert scheme. Yeah, so the limit, non-collapsing limits should be Calabi-Yau variety with log terminal singularity and with a Calabi-Yau metric, which means Ricci is 0. Yeah, so they proved everything in this paper. And well, their theorem also applies to Fano, and as far as the Ricci is bounded by both sides, so it works. So I mean, it is a bit more generous statement, but it certainly applies to this Calabi-Yau case. And as far as it is non-collapsing. Yeah. So anyway, so in roughly put, it says that in good cases, the limit of canonical metrics on, K-Einstein metrics on varieties should be varieties. So this is, yeah, very inspiring. And my observation was that it is, well, I didn't make it precise, but it's this is characterized by K-stability, and also characterized by minimizing of the same line bundle, as I wrote before. And another characterization of this limit is that, so what I meant by this equivalence is that if you consider every degeneration as a variety, so you can consider a punctured family and consider every fillings at the level of polarized varieties. And what I'm saying is that this limit, which is obtained by a differential geometric way, is characterized by this K-stability and also minimizing this line bundle. Anyway, another characterization is done by these people, and it says that this non-collapsing condition is equivalent to that it does not go to infinity distance with respect to the Weil-Petersen. So we have some modular space, and we have some metric on it. And if you have a sequence of Calabi-Yau's or the punctual family. So sometimes it goes to infinity. Sometimes it remains inside the finite distance in some same ball. So in this, this equivalence says that this non-collapsing occurs if and only if we have the sequence or the punctual family remains in this finite distance. So this P refers to the Weil-Petersson metric I wrote before. So some metric on the moduli. Okay. So as examples of these non-collapsing limits is that in abelian variety case, it does not degenerate. So this should be just the abelian varieties. But in K3 case, it's a bit more interesting. So it's the limit, this log terminal limit or non-collapsing limit is characterized by ADE K3. And in hyperkähler case, what we get is symplectic singularities. And yeah, in the sense of Bobile. Yes. And yeah, it seems I'm spending too much time on it. Anyway, so so what if we consider every kind of non-collapsing limits of those inside M, this moduli, then we can get some partial compactification. So here's a theorem by Yu and Zhang, so which depend on which follows from this theorem, the one on soon, combined with some minimal model program, semi-stable minimal model program, which says that if we correct every non-collapsing limit, it is of this form M. So yeah, these are all the non-collapsing limits. I mean the log terminal K0 ones, and then it is has some filtration by quasi-projective values. So the point is that L, this polarization is a priori just a Q-line bundle. So if we consider the non-collapsing limit, we don't know what is the denominator of the line bundle, Q-line bundle we get. So differential geometry does not tell it. So yeah, we don't have a uniform bound. So that the theorem is of this form. But recent paper by Bilka, so I was pointed to his corollary 1.6 by Junya Xu, which I sunk. So using his theorem, so he proved, so this paper deals with the boundedness of, I mean, the usual, I mean, not only of general type, but more Calabi-Yau case and other case. And in K0 case, he claimed that this is should be bounded. So he did not he did not write in this way, but this is a corollary of his work. So at least if you combine with some effective base point free theorem due to Kora and well, I mean corrected by Fujino and yeah, effective base point free theorem, we get this stationary. So as a result, we have a canonical partial compactification, which is quasi-projective. Yeah. So what I'm saying is this should stop at some point. So from some point, these should be all equal. And these are quasi-projective by the work of feedback. So yeah, we have a quasi-projective compression, which is a compression with respect to the Weil-Petersson metric. Yeah, so the examples are like this. So in abelian variety case, it does not put any degenerations. But in moduli of polarized K3 surface case, by this partial compactification, we allow AD singular ones. So original moduli of polarized K3 with a, sorry, I forgot to put, so XL with a 2D. Yeah, so we fixed this D. So originally X was only allowed to be smooth, and the moduli is some complement of Higna devices. But by VP test and compression, so we fill in the, Higna devices. Yeah, so in it is, symplectic varieties case. So we have the same story as a K3 case. So the obtained partial compactification, which is canonical, is nothing but the usual, also gonal modular varieties. So I don't have a time to explain the proof, but yeah. So yeah, so far I have been talking about partial compactification, which is just a quasi-projective, not a projective. So any questions so far? Then let me go on. Yeah, so I want to talk about, so let's consider the compactifications. So as I wrote toward, I don't have a complete understanding of the compactifications, but let me just discuss here. So if you consider a bit weaker version of K moduli in Calabi-Yau case, K-trivial case, that is to allow semi-stable, K-semi-stable degenerations. So this is just a classical conjecture or the dream to consider a projective compactification whose boundary should be parameterized by whose boundary should parameterize SLC Calabi-Yaus. And so let's call this formulation this only requiring K semi-stability. Only requiring K semi-stability, then we call it K modular. No, not the K polystable ones. Then there are certainly many classical examples which are intensively, there are so many examples and good examples, and many of them are often dominated by a toroidal compactification. So in the sense of Ashman-Rappaport type, or semi-toric compactifications, which in the sense of Professor Lowenha. And when this M, the previous partial compactification, is a case, is a certain similar varieties. Locally Hermitian symmetric variety. So the renowned example, so this AG, by which I mean moduli of principally porous abelian varieties, moduli of G-dimensional abelian varieties, is compactified to AG Voronoi. It is an example of toroidal compactification, and this toroidal compactification is not unique. It's like in the toric case, we need some combinatorial data to specify which toroidal compactification. But this Voronoi toroidal compactification is a special case of toroidal compactification, which correspond to some so-called second Voronoi fan. And these works are done by these people, and also there should be many related works. And so what about case 3 case? So this is very hot topics, and yeah, there are many examples of these weak K-moduli compactifications whose boundary parameter is SLC K-trivial degenerations. So there are many explicit examples. SHA around 80, Raza, and there's a announced work by Gross Hacking Kill Gibelt. This is to consider toroidal compactification. So this is not public yet, and I think this is still ongoing project. But yeah, they are motivated by mirror symmetry. And this Alexeyev Thompson, Alexeyev Engel, yeah. So there are many examples. Yeah, and it is more or less using the MMP method. So the main point is to each polarized variety, we consider ample Q divisor, which is inside this L, the Q linear system. Then consider the canonical degeneration of XT. Then this is a log general type with this log canonical class ample. So we can apply a similar story to KSPA and use a method of MMP to get a canonical degeneration and canonical compactification. So this is a I think this is essentially the only way to give the weak K moduli, and we can even prove that the weak K moduli should be always some example of log KSPA. Log KSPA, but I mean this way of considering the ample divisors, and but here's a problem I have to say. So the compactification really depends on the divisors you choose. So if you consider some specific K-trivial varieties, then of course there could be some sort of canonical choice or standard choice of this D. But anyhow, the compactification really depends on D. So this is observed even in the degree 2 K3 case. So Shah had a classical example of the compactification, while also recent Alexeyev Engel Thompson. So they're motivated by they use some okay, let me omit it. But anyway, they are different. There are several choices. And recently, Alexeyev Engel put an interesting paper, and they defined a class of D, which they call recognizable divisors. And what they proved is that if you consider recognizable ones, then the modular compactification should be the normalization of the modular compactification you obtain should be semi-toric in the sense of Loyenha. But the recognizable divisor should be really rare, and it requires a very hard action. And I think it's in general had to, I mean, prove this divisor is recognizable. But another thing they did is that if you sum up all the rational divisors inside this class, then it's also recognizable. And that is this paper is very interesting. And anyway, this weak chemistry depends on the divisors, and there are many choices. So what about the canonical compactification? And I only have sorry. 10 minutes to talk about. Sorry, my plan is going well. So I want to skip this. Yeah, and so my point of the remaining 10 minutes is that to still consider a canonical compactification. Sorry, let me, yeah, go back. So this compactification, which are varieties, depend on D, but we want to consider a canonical one. And let's, by applying the similar idea, following the Fano case. So in Fano case, we originally considered more differential geometrically. So we consider the limit of Kerr-Einstein matrix. And let's consider the same thing in the Calabrian case. Then the outcome is that we get a canonical compactification, but it is not a variety. It is not a variety at all, but it is still compact topological space. And furthermore, that compact topological space is somehow describable by still some algebrogeometric means. So that's what I'm going to talk. So in elliptic curve case, what we associate at the boundary is S1. So at the infinity, we associate S1, which is a limit of elliptic curves with this flat metric. Yeah, so the compactification we consider is this Gromov-Haus limit. And in case 3 case, recall that this partially compactified canonical moduli is one of similar variety. So orthogonal moduli variety. So 19 dimension. So by the period map and the Torelli theorem. On the other hand, Satake constructed finite compactifications, finitely many compactifications for each locally symmetric space like this. So his work is purely theoretic and representation theoretic, but he to each representation of the group, which is a SO in this case, indefinite SO in this case. He considered finite compactification, so which depend on the representations. The famous one should be called the Bailey-Borel compactification. So the history was that after the Satake's paper, famous paper in 60, so some years later, Bailey-Borel proved that it's in one of the Satake's compactification is projective. So in many cases, I think this is just called the Satake compactification or Bailey-Borel compactification. And the Bailey-Borel compactification, if you apply Bailey-Borel for the K3 moduli, the moduli of algebra K3, then polarized K3, then the boundary looks like this. So we have finitely many curves, which are modular curves. So the upper half plane divided by the discrete group. And also we have a 0-dimensional finite point. So so the boundary looks like this. Could look like this. Indeed, in this one case, this looks like this. The boundary looks like this. So this part corresponds to the above, and this corresponds to here. And if the K3 goes to here, then it corresponds to type 2 degeneration. And if the K3 goes to here, then it corresponds to type 3 degeneration. And if you consider another Satake's compactification, then the boundary, the partial, this round means the boundary. The boundary becomes non-variety, and it looks like this. So it replaces this point. Here I'm writing here. So replace the point by somehow real 18-dimensional quotient, and replace this 4 curves by 4 points at the boundary. Then it still gives a compactification, but and this is corresponding to a joint representation of SO, but the compactification is non-variety. In the joint work with Oshima, we used this compactification and proved that this is really the compactification, the canonical compactification we get by imitating the method of Fano case. So if you just consider the limit of K3 matrix, then we get this non-variety. And there's another way of describing Satake joint compactification, this compactification which we use. So that it may look a bit more familiar from algebra geometry perspective. The thing we do is that if you compactify a quasi-projective variety by a smooth span, with SNC divisor as a boundary, we replace the SNC divisor like this. So here we have 1, 2, 3, 4, 5 components, and we replace by its dual complex. So here we get triangle instead of this, and here we replace this 2 component by the segment. Then we can somehow take a disjoint union of this, the original interior, and the union of this dual complex, and we put a topology on it to make it a compact topological space. So this looks really a weird compactification. This is not certainly a variety, but what we show in general is that for any similar variety and its toroidal compactifications, the obtained compactification, this MSBJ, this which I call, so this kind of compactification is originated in Morgan-Sharen's work. So this Morgan-Sharen's type compactification coincide with this Lee theoretic compactification, Satake's compactification. So we have a 2 equivalent way of describing the same compactifications, which are not a variety. Okay. And the main point of this, what we logically do is from this compactification. So remember that we had remember that. So I wrote this picture here. And this interior of the boundary is 18-dimensional over real numbers, and this is the part I wrote as here. F2D of L is the isotropic line, is like here. And here we parameterize some matrices too. And at the remaining 4 points here, we associate some segment. Well, I mean, just the interval. Then what we prove, at least partially, is that these associations are continuous. I mean, so the interior corresponds to K3 surface, which are real 4-dimension, but the K3 surface if the K3 surface approaches this boundary, then this 4-dimensional manifold collapses to this matrix sphere. Yeah, that is what we proved. And we expect the same for this type 2 case. And in particular, the conjecture of Koichi-Mitch-Soiberman is proved for case-3 case. And the proof uses construction of special Lagrange vibration that we omit. And yes. And if you consider non-algebraic case-3 surfaces, then the moduli is essentially the union of all Kähler cone of case-3, which is 60 dimension. So 40 plus 20, so it's 60. But the modular hyperkähler rotation, which preserves the metric, it's 57 dimension. And we have the similar story. And we still have a canonical compactification by Satake, and we let the boundary of Satake parameterize geometric object, which I wrote here. So this is the boundary of the Satake's compactification for all the case-3 surfaces. And so the biggest strata should parameterize S2, and another strata parameterize 3-dimensional tori plus divided by the involution. Yeah, but yeah, interestingly, inside the boundary, so we get a moduli of elliptic case-3. And actually, this is the same as the Satake Borel for that. And yeah, here's another work for type 2 cases. So in the previous paper with Oshima, so we focused on the type 3 case, and we proved that case 3, we proved the result corresponding to the collapsing of case 3 to spheres. So it is for type 3 degeneration. But for type 2 degeneration, by which I mean the case when moduli, I mean the case 3 is go to this 4 point, or equivalently going to these 4 curves. So the type 2 cases. What we recently did is that we found extra data, which is a PL function from the interval. And so the function looks like this, just a PL function, and which is not differentiable at most 18 point. And so this is, so yeah, to each type 2 degeneration, so we associate some function, and the definition itself is sorry, the time is ending up, so let me so this PL density function, PL function can be seen as the additional information of the type 2 degeneration. And so maybe actually I wrote an example of type 2 cases, I mean degree 2 cases here. So in degree 2 case, the degree 2 case 3 surfaces known to be double cover of P2, those doubled projective plane, a branch that's a sexist. So, and the boundary of the Satake the very Borel compactification looks like this. And if you replace by the adjoint type compactification, then these 4 curves become 4 points. And this point becomes real 18 dimensional. And so in this case, so the expectation is that the K3 surface should limit to the segment, which is not proved yet. But what we recently observed that there's a PL function, which is of this form in this case. So yeah, it is undifferentiable, but only at 1 point. And in this case, we associate this kind of function. This case, we associate just a linear function like this. This case, we associate like this. And whose combinatorial, sorry. Whose combinatorial structure is also classified in terms of root lattices. And let me say that these root lattices appear in the work of Friedman and Scatton in 80s. This red part appears in 80s. So especially in the degree 2 case, this is written. And recent work of Alexeyev, Engel, Thompson they did some compactification of F2 as a variety. So they discussed some special case of log KSP variety, modular compactification. So it was 2 years ago. And they used as a tool this kind of how do I say? So they consider the union of polyhedron, 2 polyhedron. So each polyhedron corresponds to this P2, essentially the moment polyhedron for P2. And they consider the union of and group together to make it S2. And they use that to describe the degeneration. And their picture is somehow enhanced to this PL function. And so these are all compatible. And yeah, I wrote as a picture. And interestingly, for example, in this case, so we have EAE, and it was observation of Manin that if you consider derivative and inside the Néron-Severi, if you consider orthogonal of minus k, then you get a E-type lattice. So if you consider union of derivative surface, then and degenerates case lead to that kind of degeneration, you get this kind of E-type degeneration. But in these cases, we don't get such a, so these are different type of type 2 degenerations. And our point of our more recent work is that this PL function really appears as the limit of the matrix, the K3 matrix, the Calabian matrix on the K3. So if you just take a limit of the K3, I mean the K3 metric, then the density function becomes like this. And we don't have a full proof of that, but at least proved that it is true along some strata. Yeah, so that's a partial result. And yes, so let me, yeah, end here. Yeah, so thank you very much.
Okay, thank you very much for